Okay, so does anybody have any questions, anything you want me to go over? Nick? You're trying to be great, by the way.
Number 7.
What's number 7?
It's asking how would you generate the force to cause the spring to elongate, like in a different method?
Yeah. Don't make this complicated.
So I just said like, would you like stretch it out with your own hand?
Yeah, that's all you have to say.
Okay.
You can say, okay, hey, I wanted to stretch that same amount, which is good. So that's going to be a segue into the last question about the moments. Let's talk about that. So let's say that I pull this thing down, right, and I'm going to stretch it 15 centimeters, okay? So if you go to your graph, you can look and go, okay, hey, here's an elongation of 15 centimeters, right? It takes a certain amount of force. So on your graph, right, you could say, oh, here's an elongation of 0.15 meters. Here's your line of best fit. You're going to come over here, boom. That's going to be a certain value. So no matter if I let gravity provide that force to stretch it that far, or if I just grab it and pull it that far, it doesn't make any difference. Something has to generate that amount of force, okay? And this is going to be important. Doesn't make any difference what creates that force. That amount of force is required to stretch it that amount. Now, speaking of graph, here's the exact sequence I'm going to go through when I grade this assignment this weekend, okay? I'm going to look at your graph first. And what I want to see is I want to see like elongation here, I want to see force here, okay, that's in newtons. I want to see the points circled on the line of best fit, okay, and I want to see the coordinate pairs written on that. You're trying to convey information, okay. That's the first thing I'm going to look at. So look at your graph. Does it look like this? Do you have a couple of points circled? Do you have the coordinates written beside it? If you do, hey, you're golden. If you don't, bad things are going to happen. Now, here's the next thing I'm going to do. I'm going to come out here and I'm going to find the 1 Newton number. And then I'm going to come up here and I'm going to see where it crosses the line of best fit. And then I'm going to come over here and I'm going to see about where that point is on that elongation. Okay? That should be about what the slope of your line is, because that's what the slope of that line means. Now, speaking of calculation of the slope of the line, I want to see something minus something over something minus something equaling a slope. Okay? Do not, how are you not, in what form are you not going to leave that slope?
Fraction.
As a fraction. No, bad. Okay? Now, typically, on these springs, typically the slope is around 0.01, 0.02, something like that. Okay, that's typically where your slope is going to fall. So if that's where your slope is, you're cool. If you have a slope of like 15, that's bad. Okay, right? So it's typically going to be a decimal, generally pretty small. So I'm going to come in here. I'm going to find the 1 Newton mark. I'm going to come up here. I'm going to go over. I'm going to find that mark. That's about what your slope is, because that's what that means. So here's the big shift that you have to make when you look at graphs in a physics situation. You're going to come over here, and first off, what units should you have on that slope?
Meters per newton.
Meters per newton. Okay, so this should be meters per newton. So let's say you got an answer of 0.011. Okay? And Haley, that's what you got, something like that. So let's say this is the slope that Haley got on her line, 0.011 meters per newton. So here's what, you have to understand what this number means. This means that for every 1 Newton of force that I apply, this is how far it stretches. Okay, that's why you have to have the units on it. Because if you just have a slope of 0.011, okay, big whoop. I don't know what it means. Okay, is it like, you know, hairballs per year on your cat? I don't know. Okay. If you just have 0.011, you convey no information. But as soon as you put the units on it, then you're going, oh, now I know what that means. And the other thing is, and we'll spend more time talking about this today, I want to see how you generate this. Because if you have all these numbers up here, and then you get down to the end and go, oh, Burkamp says it's really stressed this idea of units on the end. I better put units here. Well, if you don't know what's happening up here, you don't know what units to have down here. Okay, so this is why you have to view this as paying attention to those units so that you see what you end up with here in terms of a slope. Now, go up above. Did this graph start at 0, 0?
Yes.
Yes, because with no force you get
No.
no elongation. So your general form is y equals mx plus b. What is your b value?
0.
0. Do not have a y-intercept. Okay? Don't have it. There is no y-intercept. Now some of you might have plugged these numbers into your calculator and your calculator generated the line and your calculator generates a small y-intercept value. No, you don't have a y-intercept value because it goes through 0, 0. You know if you apply no force, you get no elongation. Okay? So if you plug these numbers into your calculator and had it do the regression, don't. The calculator lied to you, okay? I know that's shocking. Monday, I'm going to spend about half the class proving that your calculator lies to you. And you're going, no, my calculator's never lied to me. Yes, it does. Okay. Now, let's talk about that question about if you had like the stiffer spring, okay? And how much, what would happen? And I say, here's what you want to do. You want to use the phrase forgiven. So here's the deal. In most labs, you're going to have two variables, okay? Two variables. You're going to have, in this case, elongation, and you're going to have force. So when you answer a question like that, you want to focus on keeping one variable constant and changing the other one. Okay, so when you answer this, here's how you don't want to answer it. Don't sit there and go, well, if I've got a stiffer spring, then for more elongation, that requires more force. Or for more elongation, there's less force, something like that. You're changing both variables. And then you don't know, then your answer just doesn't make any sense. So in this answer, here's what I'm looking for. You want to choose either to keep the elongation constant or to keep the force constant. I don't care which one you pick, but pick one, okay? So you could say, hey, for a given elongation, and let's say it's 0.1 meters, whatever it is. You would just say for a given elongation. So in other words, I want this spring to stretch a certain distance. What's going to happen to the amount of force that that's going to take? It's going to increase, right? So for a given elongation, that's going to require more force. The slope is going to become smaller, okay? The other way that you could say it is that you could say for a given amount of force, what's going to happen to the elongation? The elongation will be less, and that's going to flatten out the slope. So don't say this. Don't say for a given spring. That isn't where I want the words for a given. You want to say either for a given amount of elongation or for a given amount of force. You want to focus on keeping one of those two constant and then looking at the impact on the slope. Everybody cool with how I want that answered? Okay. Now let's talk about the moon question. Okay? Talk about the moon question. So there's three possibilities on the moon question. One is that the slope will be less steep. One is that the slope will be more steep, or the slope will just be the same. Okay? So those are your three wild cards. Less steep, more steep, same. So how many have that the slope is less steep? Nobody has the slope is less steep.
What number?
Wait, for what?
That last question on the back. About if we did this at the moon. So the slope could be more steep, less steep, or the same. So nobody has the slope is less steep. How about you do?
Yeah, I do.
I think I do.
Okay. All right. What's that? For God's sakes, you're American. You get to vote. There's no chance of you being shot for voting. Okay? Okay. How many have the slope is going to be more steep? Okay. We got a handful there. McGriddle over there. That might be Grape and McGriddle. Yeah. And how many have the slope's going to be the same? Okay, well, let's talk about this. All right. So let's say we go to the moon. Ultimate field trip, right? So we go to the moon and we have this 1 kilogram mass. Now, you have to understand what creates gravity. So this is not to scale, but here's the Earth and here's the spring, and here's the 1 kilogram mass. Okay, like I said, this drawing is not to scale. Okay? And what creates gravity is this. Every electron, proton, neutron that makes up this 1 kilogram mass here is attracted to every bit of matter that makes up the Earth. And as human beings, not only have we invented McGriddles and great Gatorade, some of our finer moments, okay, we've also made some major scientific discoveries, and we said, hey, oh, there's a gravitational force. We can calculate that. And we say that what something weighs, and again, in a physics classroom, when I'm talking about weight, I'm talking about a force which is going to be measured in newtons. Okay? So when you see weight, you think newtons. Okay? Not kilograms, not pounds, newtons. Okay? And on Earth, we take a 1 kilogram mass, and we multiply that by 9.8 meters per second squared, because that's the acceleration due to gravity. And you get 9.8 newtons. So 1 kilogram mass on Earth weighs 9.8 newtons. So, which is, let's just round it to 10. So somebody look on your graph, and what was your elongation for about 10 meters? Ballpark. Just find the 10 Newton mark, go up. What's your elongation, roughly?
0.11.
0.19?
Cool.
1?
0.17.
0.17. Okay, let's go with 0.17. Okay, so I take this, I hook it up. This is interacting with every particle that makes up this the big rock that we're on. Sum total 9.8 newtons. It stretches about 0.17 meters. Okay. Now, gravitational acceleration on the moon is only 1.6 meters per second squared. So now we're on the moon, and we're doing this lab again. So we do this lab on the moon. We still have a 1 kilogram mass, but now we're multiplying it by 1.6 meters per second squared. So now I get 1.6 newtons. So the 1 kilogram mass isn't exerting, because of a weaker gravitational field, it's only exerting 1.6 newtons of force. So what's going to happen to that whoa, it's weird. What's going to happen to that amount of elongation? It's just like, is elongation going to be the same or less? Less, right? Because it's going to, you put that on, it's going to be like, that's all the farther it's going to stretch. But, go back to your graph. And this is why it's important you understand what you graph. So, here's 1 newton, here's 2 newtons. So your graph, the far end of the graph on the moon, is only going to end up at 1.6 newtons. So here's my point. If I go to 1.6 newtons and come up here, I'm going to have a certain elongation. And it doesn't make any difference how I generate that force. Whether I use a spring to do it, or whether I use a weight to do it, or I grab my hand on it, pull it down. So your data is going to be really, really crunched together. Okay, you're not going to have very much deviation on your data. But the graph itself, the slope is going to be the exact same. Because you have plotted force and elongation and not mass and elongation. Okay? So because it's force, you're not going to have, your data points are going to be really crunched together, but the slope is going to be the exact same because it's the same ratio of force to elongation. So if your answer is wrong, fix it. Okay? Fix it. Okay. Anything else? Going once. Going twice.
Oh.
Whoa.
I had a question about like the way the force elongates the spring.
Yep.
Is it the same amount of force like how would you calculate the force to compress the spring?
It basically,
Would it be positive or like?
it just depends on how you define it. But yeah, so if I'm like this, right, and I can, like, let's say it took a certain amount to compress, to stretch it this far, it's going to take that same amount of force to compress it that far on the other side.
Oh, okay.
So but the problem is on compressions, once it hits solid, you can't compress it anymore.
Okay.
But yeah, it's called the spring constant, and we'll talk more about that later. It doesn't make any difference if you compress it or if you stretch it. It's the same ratio.
Oh, okay.
Yes, ma'am.
So I'm confused about the moon question.
Let me unconfuse you.
Okay, so you're saying that it would be the same slope?
The slope would be the exact same, because it's the same proportion of force to elongation. So it's going to take me the same amount of force to stretch this spring if I just grab it and pull it down. Whether I'm on the moon or the earth, it's not going to make any difference. Okay? But on the moon, if I use those exact same mass sets and put a 1 kilogram mass there, it just won't stretch it as far. But it's going to stretch it to the same ratio that it does on Earth.
Okay, so what does gravitational acceleration mean then? Like, was that just put in there?
No, yeah, but that's the whole point, is that it won't stretch it as far, okay? But it's still going to be the same ratio of force to elongation.
Like no matter
How,
what.
if you're applying the same force but it doesn't stretch as far?
No. No. Don't confuse mass and force, okay?
Okay.
So if I'm on Earth and I say, okay, hey, I want you to stretch this thing 10 centimeters. It's going to take you a certain amount of force to stretch it 10 centimeters. Now, you're on the moon, and I say, hey, stretch it 10 centimeters. It's still going to take the same amount of force. Okay? So on Earth, we're letting this interaction with the gravitational field stretch it. Okay? But if I go to the moon, since there isn't as much gravitational force, it won't stretch it as far, but it'll stretch it to the same ratio than it did on Earth. So if you want to complicate things a little bit, if all you have on the moon is a set of masses and you want it to stretch, what happens to the amount of mass that you would have to put onto it? Yeah, you'd have to put a lot more mass to get it to stretch because you don't have as much of gravitational acceleration. Okay, now are we good?
Yeah.
Going once, going twice, sold. Okay, when you guys hand stuff in, I've got like a stapler that's hanging there from the ceiling. I've got one generally on my table. All of your stuff goes into the second tray down. This is going to require a little bit of thought because you're in third block, but my second block is my plan. But I've got a little label on the outside. So all of the stuff that you hand in goes in that second tray down. So, Max, here's what I got. So up there at the top, what I want is all you have to do is write down the units that we're putting in for distance, mass, velocity, time. I don't want, like for distance, I want meters. Don't put the variable. Don't put like D for distance or X or something like that. So like up there where it says distance, just put meters. That's it. That's all you have to do. Now, on the force one, let's make sure everybody's cool on the force one. So on the force one, what are your two options for the units of force? Newtons, capital N, right? Or
Kilograms, meters per second squared.
kilograms, meters over second squared. Now, if by a week from today, when you have this first big test, make sure that you have these 3 fundamental units and these 3 derived units solid. Okay? Solid. Make sure you should not have to give them any thought at all. Write them on your best friend's forehead so when you look at them, you know, oh, here it is. Okay, that's a bit extreme. But now, on the next part, down below where I've got like velocity times time, v squared, I'm going to show you how I want this one done. Okay? So in dimensional analysis, the first thing that you do is you write down the units for the variables. So I'm going to work number one, make sure everybody's cool. So number one, down below, I've got VT. So here's the first thing that you do, is you substitute in the units that everything is measured in. So velocity is measured in meters per second. Beautiful. Time is going to be in seconds. So this is what I would expect. I want to see this stacked, okay, multiplying it by seconds. So what's going to happen to the seconds? Those are going to cancel out. Again, this is a process. You want to show things canceling out if they do. And you're left with meters. So this is what I want on number one. Okay? This is what I want on number one. Now, if you look down on number two, let's talk about number two where I have v squared. Because that's one of the most common things that gets squared is velocity. So I got v squared, right? Velocity is in
meters
per second. So what you want to do is write that as meters per second times meters per second. Okay? Hold on. Got an extra 2 there. Oh, come on, erase. Okay? So that's meters per second times meters per second. Or if you want, you can just put meters per second squared. I don't care which one, but just put one of those two. But here's the point. When I take meters per second times meters per second, I get? Yeah, I get meters squared over second squared. Make sure that you're squaring both parts of those. Now, let's talk about number 5. Down there, I have m times m. What do you think I want multiplied together? There's 2 options. On number 5, do you think I want meters times meters? Or do you think I want kilograms times kilograms? Kilograms times kilograms. If I wanted you to put in meters, what variable would I have put there?
D.
Yeah, like a distance, an L, something like that. Okay? So this is the most common mistake that's made. So on number 5, when you see m times m, that is kilograms. It's mass. So on that one, this is the calculation that we're going to do when we do Newton's laws of gravity. We're going to multiply 2 masses together. So you have m times m, so that's going to be kilograms times, which should get you kilograms squared. Okay? So finish that top part, finish all the way through number 7. So, Max, stop that. Okay. Now, I'm going to show you exactly how I want number 1 at the bottom written. So here's the biggest thing that I'm going to have to get you to fight, okay, and realize, is that in algebra 1, algebra 2, whatever, what you do is that you put in the numbers and then you solve the equation, okay? It's a train wreck, okay? It is not how physics is done. In physics, you always want to solve the equation for the variable first, and then your last step is to put in the numbers. So if you look at like any physics journal, anything like that, you never see numbers. All you see is variables. The numbers are the last step in the process, okay? Because we don't care about the product unless the process is there. So let's say that you've gone through and you solved this equation. And this equation looks cool, right? Oh, V equals V naught T plus A. So let's make sure everybody remembers. How is this V naught different from that V? This is the initial, right? So let's say McGriddle over there is initially moving at 10 meters per second, right? Okay? And then he realizes McDonald's is about to close and he's got to get there. So he punches it up to get to 15 meters per second. Okay? So we're going from 10 to 15, right? Okay. So, are they going to be in the same units? Even though they're different velocities? Yes. Okay. And so, and if you walked up to 99% of Americans and you said, oh, V equals V naught T plus A, and it's like, oh, you can speak physics. You're smart. Okay? Nobody would realize that the equation could be wrong, but you're just going to say, oh, V naught. As soon as they hear that, like, wow, you're smart. Okay, so here's what you do in this process, is that the first thing that you do, just like you've done up above, is you substitute in the units. Okay? It's the first thing that you're going to do. It is a process, not a product. So, I'm going to have meters per second equaling meters per second times time plus an acceleration in meters per second squared. Okay? So I've got meters per second equaling meters per second times, hold on, let's get that up. I said that and then I wrote the wrong thing. Times seconds plus meters per second squared. So that's, yes?
I was wondering, like right away, when you say seconds, can we put it over 1?
Yeah, like this? Oh yeah, if you want
Just
to do
like
that.
right away?
Yeah.
Okay.
Oh yeah, right from the get-go. If you want, if that makes sense to you, go. Yeah, fine, great, grand.
All right.
Yeah, no worries. Okay. Now, what's going to happen here when I multiply this together? I'm going to get what? Meters. So up here, I've got meters per second equaling, this is going to cancel out, meters plus second squared. So here's the $1 million question for the trip to Hawaii, $5,000. Maybe not. So can I take a distance? And this is fundamentally what I'm asking. Can I take a distance, add it to an acceleration, and end up with a velocity? No. For any number of reasons, this is a train wreck. Okay? Stop the bus. This dog ain't going to hunt. I don't care what little acronym that you want to put it. This is a train wreck. Now, it looks cool. Okay? It looks very cool. But at the end of the day, this equation will not work. But again, here's what you all are going to do. You're going to put in numbers into your oracle, and you're going to go, oh, that's 8 plus 2, and then you're going to say, oh, the answer is 10, because Burkamp wants to know the final velocity of McGriddle as he's driving to McDonald's, and don't pay any attention to the units, and then all of a sudden, you're going to write down 10, and then you're going to put meters per second on the end of it, and then I'm going to look over it and go, really? You took a distance and added it to an acceleration and got a velocity, and y'all are going to go, oh, that doesn't work. It's like, you're right, it doesn't work, because you just focused on the answer without paying attention to the process. Okay? All right. Now, one of the things we'll do a lot is calculate acceleration. And the simplest way to do that is A equals V minus V naught over time. So when you have a situation like this, let's address what's going to happen here. V is going to be in meters per second minus meters per second divided by time, which is in seconds. Now here's what I don't want you to do. Here's what I don't want you to do. Don't look at this and go, oh, meters per second minus meters per second, I get 0 over seconds. I don't have any units at all. This is cool. No. Do I get 0 out of this? No. I don't know what the numbers are. But here's what's important. All I know is that I can take meters per second and subtract meters per second from it. And when I do that, what units do I end up in? Yeah, I still get meters per second. So if you have a situation like this, and you will, you just go, oh, that's meters per second divided by seconds. Okay? So when you subtract this, don't go, oh, that goes to 0. No, that's not what happens. Or let's say you're doing an average, and if you add them together, don't put, oh, meters per second plus meters per second gives me like 2 meters per second. We're not adding variables. We're just showing that the units can add up to get to the same point. Okay? Now, on the back side, flip that over. These you're going to do on your own. So, what you're going to do on 2 through 8, you're going to go through and you're going to tell me basically, are these equations valid? Now, let me give you a hint. So, like if you look on number 3 where it has x equals v squared minus v naught squared over 2a, don't even worry about that 2. It's not going to change the units. It'll change the numeric answer that you get, but it will not change the units itself. So I wouldn't even worry about that numeric value of 2. The same thing on number 6 where you have 1/2. Don't even worry about it. Now, let me give you some hints. When you get down to number 7, okay, where you have time equals mv over f, on that force, okay, on that force, do not use newtons. On that one, what you want to do is put in the kilograms meters per second squared. Because you can't cancel out like kilograms and newtons, but you can cancel out kilograms and kilograms meters per second squared. Okay? So on number 7, on that force one, do not use newtons. Use kilograms meters per second squared. So what you want to do on all of these, substitute, here's your process. And again, it is a process, okay? Not about writing down variables and then a miracle happens and oh, it's valid. So what you're trying to prove on all of these, and this is basically a proof, you're trying to prove whether these equations are valid or not valid. Most of them are valid, okay? Most of them are, but not all of them. So your task is to go through and take these and at the end of the day, number 1, show how things cancel out. When in doubt, when you're dividing, anytime you're dividing, I would recommend multiplying by the reciprocal, okay? Because that's easier to show how things cancel out. That's my recommendation. You don't have to listen, but that would be my choice. So, we do this right quick. We're not done. There's still more stuff to go, okay? But go ahead and work on this, and then when you get this done, get that handed in. If you're not sure if you're doing it right, this is the time to ask me and go, wow, Burkamp, am I doing this right? And I am more than willing to tell you yay or nay. All right? So, make it happen. So, shut that down. You're so excited that it works every time. It's like, oh, it worked. Technology is cool. Okay, so here we have, oddly enough, a marble launcher that launches marbles. Okay, I've asked for a freshman launcher. They won't let me have one. I don't know why. I think it would be cool. I've also asked for a particle accelerator, and they won't let me have that either. I was like, come on, we could be the only school in America that has our own particle accelerator. How cool would that be? It's only like 25 million. Okay, we could put it underneath the football stadium. It would be cool. You know?
What does it do? Isn't that
Accelerates particles.
Isn't that just heat?
A particle accelerator?
Yeah.
No. You take like individual protons and get them up to like the speed of light, and then you smash them into other protons, and you see what goes flying off. Yeah.
Wow.
Yeah, come on, man.
The level of intellectual conversation was here, and then like, don't you watch The Flash? And then it was just went, what?
So when you see something happen, like if you put it under the football stadium, will the football stadium move or something?
No.
You can't see anything, right?
No. You have a bunch of detectors that, because you're making quarks go flying off. You can't even see the individual protons.
I was gonna say, you can't see anything.
Yeah, it isn't like we're taking two apples and making them go around and just smash them. We have like a camera and a live feed as the apples. Particle accelerator? No, we have apple accelerators. Damn it! Come on. Okay, we're just that cool. Okay, anyway. Yeah, we're just that cool. All right. Okay, so I got my marble launcher, and I like how the safety protocol says, you know, always wear eye protection and never launch marbles at people. Whatever. Okay, so I've got two variables that I'm going to look at, okay? And when I pull this down, I'm exerting a force over distance. So this is like compressing a spring, okay? There's a spring in there, and now I'm forcing that spring to get compressed. So what I want to look at is a relationship between force and the acceleration of the marble at the point of impact, okay? At the point of impact. So I can pull it down a little bit, right, and let go of it. Boom, okay? It goes flying off. So what I'm doing is also storing the concept of what's known as potential energy. And you'll hear me say this again and again and again, but Mother Nature and potential energy don't like each other, okay? Maybe like in middle school, they wore the same dress to a dance, or they both tried to, you know, I don't know, date the same boy, or somebody posted something on Instagram. I don't know. They hate each other. Because as soon as you store potential energy and then you let go of it, it automatically changes into kinetic energy. The same thing is true. If I lift the marble up, I store potential energy. As soon as I let go of it, it changes into kinetic, okay? Mother Nature likes kinetic, doesn't like potential. And there's no hesitation. It isn't like, you know, you stretch your rubber band, okay, and you're storing potential energy. As soon as you let go of it, what happens?
Back.
Boom, it goes flying off. It isn't like Mother Nature even hesitates. It isn't like you let go of the rubber band, which would be cool. You let go of the rubber band and it hovers there for a couple seconds before it like takes off. It's like you let go and it just sits there and then all of a sudden, boom, okay, it goes off. No, Mother Nature and potential energy do not get along at all. Okay, we don't know why, but they just don't like each other. So, I've got two variables. I can control how much force I apply, and then the acceleration of the marble at the point of impact. I'm not talking about the gravity acceleration. Okay, that's a fixed value. So if I pull it down even farther, okay, right, I get more acceleration. If I max it out, right, like that one. Not bad for an old man. Okay, cat-like reflexes. Okay, huh? Why? It's not going to do anything. For God.
Oh, yeah.
That broke. I was going to feel really bad. Okay, thank God. Good. what happened? I don't know. I was just lecturing and all of a sudden it's just shattered. Okay. So, we're going to graph force and acceleration. So where are we going to put force?
Along the
The
x-axis.
Why?
Because it's the independent variable.
Why is it the independent variable?
Because we manipulate it.
Yes, we can control how much force we apply to the marker. So force is going to go here, right? Now, I would reckon you'll see why this in just a second. I'm going to put kilograms meters per second squared, and you'll see why in just a second. So over here, I'm going to put acceleration. Michael, what units is acceleration measured in?
Meters per second squared.
Beautiful. Meters per second squared, okay? Is this graph going to start at 0, 0?
Yeah.
Yeah.
Why?
Because when there's no force,
No force, no acceleration. What do you think the graph is going to do? Move. Words. Words. Move.
It's gonna have a
Okay.
pause.
Maybe something like this. Linear? Let's go with yes, this will be linear. So we can find the slope, right? Change in y over. So I got meters per second squared divided by kilograms meters per second squared, right? So what you're going to do is you're going to draw this graph, okay, if you on that assignment that I just gave you. You're going to draw this graph. You're going to find this slope. Now, here's the short answer. When I do this, what's going to cancel out? Right? So what are you left with?
Kilograms.
I'm not left with kilograms. I'm left with 1 over kilograms. Now, if the units had been kilograms, what do you think the slope represents? If it had been kilograms, the slope would represent mass. But since it's 1 over kilograms, it represents the inverse of mass. So down below, on that first question, okay, down at the bottom, this is what I want done here. And this is what you're going to end up with, is 1 over kilograms. I'm going to ask you, what does the slope represent? And you're going to tell me it's the inverse of mass because it's 1 over kilograms. Okay? Now, over on page 2, here's the second graph that you're going to have to draw. You can just get one sheet of graph paper and divide it in half. You got some questions to answer along the way. On number 12, you're going to draw a second graph. On the second graph, time always goes on the x-axis. Time always goes on the x-axis. Over here, you're going to plot position in meters. Graph's going to look something like this, and then you've got some questions to answer over here on this side. Go fly, be free, have a great weekend. There we go.